A statistics professor plans to travel to a conference by plane. When he passes the security check, they discover a bomb in his carry-on baggage. Of course, he is hauled off immediately for interrogation. I don't understand it, the interrogating officer exclaims. You're an accomplished professional, a caring family man, a pillar of your parish, and now you want to destroy that all by blowing up an airplane. Sorry, the professor interrupts him. I had never intended to blow up the plane. So for what reason would you try to bring a bomb on board? Let me explain. Statistics show that the probability of a bomb being on an airplane is 1 out of 1,000. That's quite high if you think about it. So high that I wouldn't have had any peace of mind on the flight. And what does this have to do with you bringing a bomb on board the plane? You see, since the probability of one bomb being on my plane is 1 out of 1,000, the chance that there are two is 1 out of 1,000 times 1 out of 1,000, or 1 out of 1,000,000. If I already bring one, the chance of another bomb being around is actually 1 out of 1,000,000, and I am much safer. So we are delving into probability and actually into the general product theory there. And so a random phenomenon is a situation in which we know what outcomes could happen, but we don't know which particular outcome did or will happen. Okay, so for any random phenomenon, each attempt or trial generates an outcome. So the outcome is what happens during the trial. So we're going to go ahead and do a random experiment where we have a spinner, and I created it for Cedar Ridge colors, purple, silver, and white. Then I couldn't do black, so I did white and silver, or gray, and I set those both to 25%. So based on these areas, you would predict that, let's say I did a total of 4 spins, I would have 2 purples, 1 white, and 1 gray, right? So that's what I would predict. And on 1 spin, I would get a 50-50 shot of getting purple. So let's see what happens when I went ahead and played with this spinner. So here we go. Purple, that's fine. Let's do it again. Purple, wait a second, I'm at 100%. The next one can't be purple, but it is. Well, not the next one, we won't have another purple. Got another purple. The spinner must be broken, don't you think? Let's try again. Okay, we got another purple. We got 100%. And another purple. 6 purples in a row. Wow. Finally, we got a white. Okay, it'll settle down now. Wait, we got another purple. And then a purple. I thought we were going to get a gray on that one. And a gray finally. So the thing is, this is not behaving very well. Why is that? We've only been doing 1 spin at a time. Now when we start adding more spins, you can see that the percentages are getting much closer to the predicted. Let me add 1,000 spins. And in the long term, yes, I got purple 50% of the time, and the white and gray each about 25% of the time. So it behaved. So the point is, when you're looking at individual events, probability is great, but it's not going to tell you for sure what's going to happen. It will give you a very good rough idea of what will happen in the long term if things are behaving as they should. So, can you predict what the next spin will be using probability? No, you cannot predict individual spins. But the law of large numbers says that the long-run relative frequency of repeated independent events gets closer and closer to what we think it should be like. So closer and closer to the theoretical. So how do we interpret probability? Here is a framework you can use. It says if you take a very large sample of whatever, about whatever percentage of the time they tell you, they will be whatever was predicted. So what does it mean that the probability of purple is 50% for our spinner example? If you take a very large sample of spins, in this case we were doing several hundred, over 1,000, about 50% of them will land on purple. And notice we say about 50%. We don't say exactly 50%. The common misunderstanding of the law of large numbers is that the random phenomena are supposed to compensate for whatever happened in the past, and that's not true. So if you're flipping a fair coin and heads comes up on each of the first 10 flips, what do you think the chance is that tails will come up on the next flip? Well, if you thought the coin was unfair, you might say, oh, it's like 0%. It keeps giving heads. But if it's a fair coin, it should be 50-50%. The coin does not remember the prior flips. So let's go ahead and imagine an urn with 4 marbles, 2 red, 1 green, and 1 white. And we're going to make a sample tree to determine the outcomes of drawing 1 marble. So we could draw one of the reds, the other red, the green, or the white. Really, I have 3 outcomes. I could either get a red, a green, or a white. Not all of those are equally likely. The red is twice as likely as the green or the white. And that's fine that they're not equally likely. Now, this is called our sample space. If all outcomes are equally likely, then I just have to count the number of successful outcomes divided by the number of total outcomes. So if I counted the 2 reds separate, and I say there are 4 total outcomes, then it will work out fine. So since it's always a fraction, that means the probability can only take values between 0 and 1, or 0% and 100%. So let's go back to that urn. And what is the probability you draw a green marble? Well, there's only 1 green marble out of 4. So it's 1 out of 4, or 0.25, or 25%. We can actually fill in the probability model for the urn. And the probability of red, we said, was actually 50-50, because there are 2 red marbles, 2 out of 4. Green is 1 out of 4, and white is 1 out of 4. What do we get when we add them all together? We get 1. Which is exactly, I mean, sometimes if you're doing from observation, it might not be exactly 1. It'd be like 0.99 something or 1.01 something. But it's very, very close to 1 when you're doing observed. So basically, the probabilities for all possible outcomes on a model where we know the theoreticals must add up to 1 or 100%. So let's go ahead and talk about the probability of not getting something, and that's called the complement rule. The set of outcomes that are not in the event A is called the complement of A, and it's denoted as A of C. It can also be denoted as A prime, so you might see that sometimes, little half quotation mark. Basically, the probability of the complement is 1 minus the probability of the event. So the complement is what completes the event. So if we say probability of rain, then the complement would be not rain. If we say probability of a green marble, then we'd say, oh, it would be not green, which would be red or white. So our formula is probability of the complement is 1 minus the probability of the actual event. So what is the probability you do not draw a green marble? So we would say it's the 1 minus the probability of a green marble, and we know the probability of green is 0.25, and we get 0.75. So 75% of the time we should not draw a green marble. Let's look at another example. The traffic signal to cross A.W. Grimes at Gaddiskull Road has the following timing sequence: 20 seconds green, 62 seconds red, and 3 seconds yellow. What is the probability the light will be red when you get to the intersection? Well, how many seconds are red? 62 out of a total of 85 seconds. And we can change that to a decimal. It's about 0.729 or 72.9%. So what's the probability it won't be red? Well, we'll just go 1 minus that probability we just got, and we get 0.271. All right. So now let's go ahead and look at compound events where we have something happen and then something happens. All right. So we're going to imagine the same urn with 4 marbles, 2 red, 1 green, and 1 white. And we're going to make a sample tree to determine the outcomes of drawing 1 marble, looking at it, and putting it back. So we're not going to worry about dupes so much. So I'm going to go ahead and show the red, red, green, and white. Okay. And if I complete the sample tree, probability of it looks the same on the second as it does on the first. So if it's independent, it's like, oh, the first outcome didn't affect how it looks again. It looks kind of the same, like you reset it. So with dupes, how many outcomes are there? Well, they're really all of these. There's 16. So you have red, red, that's that one. Red, red, that's that one. Red, green, red, white, etc. So we have 16 outcomes. How many outcomes had a green marble first and then a red marble? Well, we can see that there were two, all right? Two outcomes. So what is the probability you draw a green marble on the first draw? Well, it's just going to be this one right here, which is 1 out of 4, all right? What is the probability you draw a red marble given that you drew a green marble? So what it's saying is we already know we actually went down this path. We pulled a green, and then we put the green back, and what's the probability we're going to get a red? Well, if you look at the green branch right here, so we know we traveled down this green branch. What's the probability the next marble's red? Well, it's 2 out of 4, or 1/2. And then what is the probability that he draws a green marble, then a red marble? Well, there are 2 outcomes out of 16, or 1/8. But here's an interesting thing. What if I just multiplied that probability times that probability? I could take the 1/4 here times the 1/2 here, and I get the same answer. It's 1/8. So the same way we were multiplying to find number of ways to do something with a tree diagram, we can actually do that with probability too. So probability of the first event times the probability of the second event. Now it gets interesting if I keep the marble, because if I keep the marble I draw in the first draw, the urn is no longer reset. It is changed by what happens. So these are going to be dependent events. So how many outcomes? Well, first of all, if I'm keeping the marble, I have to adjust the tree. So you don't want to draw this whole tree. You need to take out some branches. So I'm going to take out the first red on that first set there, then the second red here. I can't draw green and green because I already took the green out, and I can't draw white and white. So how many outcomes do I have now? Well, I only have these. And you'll see I only have 12 outcomes. Red, 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 green, red, white, then red, 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 green, red, white, green, red, green, red, green, white, white, red, white, red, white, green. Okay? So there are only 2 outcomes that are green first and then red. So what's the probability he draws a green marble and then a red marble? Well, there are 2 outcomes out of 12. So it's a little different than what we had before. Before it was 2 out of 16. Now it's 2 out of 12. And when I simplify that, I get 1/6. So let's look again. What's the probability he draws a green marble? Well, it's just 1 out of 4 like it was before. But this one changed. The probability of drawing a red marble, if we drew a green, actually goes up. It's not 1/2 anymore. It is 2 out of 3, all right? So depending on which one of these paths you take, that affects the probability of getting the red marble. So I'm going to put 2 out of 3 there. So let's see if multiplying these works again. So if I multiply them, I'm going to write the probability of green, then red, is the probability of green times the probability of red given green. So before, the reason I'm writing red given green, well, first of all, the probability of green is always 1/4, right? So I don't have to be specific. But the probability of red here is just 1/3. Here it's 1/3, there it's 2/3, and there it's 2/3. So I have to explain which situation am I talking about. Well, I'm talking about the situation where I drew a green one first. So green is given, all right? And so when I substitute in my 1/4 and my 2/3 and multiply, 1 times 2 is 2, 4 times 3 is 12, simplify, and we get 1/6. And so you can see that we can do multiplication of the probabilities as long as we're cognizant of what was given, all right? So if A and B are independent, then the probability of B does not affect probability of A and vice versa. Every time you do something, you are resetting the machine back to where it was originally, so nothing changed. So that means the probability of A given B would just be the probability of A, because it doesn't matter if B happened or not. Probability of B given A is just the probability of B, because it doesn't matter if A happened or not. Usually, events that occur without replacement those are the ones where it's not a reset because you've taken something out of the system, and those are dependent. So let's take a look at some examples. Which set of events is dependent? Well, drawing a marble from an urn and replacing it and drawing a second marble, we've kind of reset the system. So that's independent. Rolling a die and drawing a card, card's not affected by the die. That's independent. Drawing 2 marbles from an urn. Well, after we take out that first marble, the urn is 1 marble short, so we've affected our probabilities. It's dependent. And rolling a die twice. Well, luckily, the die should not remember anything, so it's like it's reset to normal. That's why we shake it, and that's independent. Rolling a die and flipping a coin, independent. Drawing a card and flipping a coin, independent. Usually when they're 2 very different things, they tend to be independent. Flipping a coin twice should be independent. If I draw 2 cards from a deck, my deck now has 1 less card for the second card, and that's dependent. So the multiplication rule of probability, which is what I've been talking about, is for independent events, you can say, oh, probability of getting A and then B is just the probability of A times probability of B. But if it's dependent, then you have to say, oh, that A, I'm going to go ahead and that's fine because the system is reset right there. But B, A changes the system somehow. So I have to adjust the probability of B because A happened. So let's look at some examples. If we know probability, we can use the rule to make predictions, all right? So we have the batting averages for the Round Rock Express players. Carlos Peguero is 0.667. This is from an actual season when I went to a Round Rock Express game. Jake Smolinski, 0.600. Tyler Pasternicki, they have some interesting names, 0.600. Tomas Teles, 0.33. Kyle Blanks, 0.327. Ed Lucas, 0.325. And Hanser Alberto, 0.302. And Thomas Field, 0.298. Those are some pretty good batters because almost every single one of them is batting above 300. 0.300 is 300. And Carlos Peguero seems to be having a very good year at 0.667. Must be early in the season. Well, are these probabilities of getting hits dependent or independent? Well, if they're good baseball players and they don't let the player in front of them affect them, then we're going to say they're independent. All right? If that's not the case, well, then it gets complicated. All right. The first 2 batters for the 3rd inning are Carlos Peguero and Tomas Teles. Calculate the probability that Carlos gets a hit and Tomas does not. So that's going to be the probability of Carlos getting a hit times the complement of Tomas getting a hit. So it's 0.667, and 1 minus 0.33 is 0.67. Multiply both of those together, and we get 0.440. So about a 44% chance of that happening. Now we got the first 2 batters for the 9th inning are Hanser Alberto and Kyle Blanks. Calculate the probability that both of them get a hit. Well, Hanser's is 0.302 and Blanks is 0.327. So if they're independent, we can just multiply them together and get 0.099. So it's pretty straightforward. What is the probability of rolling an odd number on a die and flipping heads on a coin? Are the probabilities dependent or independent? Well, they're independent because the die and the coin don't affect each other. So the probability of getting an odd and then times the probability of getting a heads is what we're trying to calculate. There are 3 odd numbers on a die out of 6, and 1 out of 2 sides is heads on a coin. So we get 3 out of 12, or 1/4. And again, it's independent. Outcome on a die doesn't affect the coin flip. How about what's the probability of spinning purple 6 times in a row if it takes 50% of the spinner? So remember, when I was actually doing that simulation at the beginning of this lesson, I got purple 6 times in a row. What are the odds of that? Well, every time I spin, it's got a 50% chance, or 1/2. So I'm going to multiply 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2, which tends to be the same as, as 1 out of 64. And it's only a 1.5% chance of that happening, 1.6. So it's pretty low, pretty low. That was unusual to get that, but that was fun. All right, now let's go ahead and look at a case. These were all independent because the first event did not affect the second. All right. So let's go ahead and take a look at our survey about people who like cats or dogs. So first of all, we're going to start with the very simple probability of just one person. So we're not getting into compound events yet. So I surveyed my class and I had 15 students who like cats and like dogs. I have 5 students who like dogs but don't like cats. 1 student who doesn't like dogs but does like cats, and 4 students who don't like cats. How many students did I survey? Well, I'm going to total up the number that like dogs and don't like dogs. So that would tell me 25, right? Let's do the ones that like cats, 16, and the ones that don't like cats. Oh, yeah, it's definitely 25 that I surveyed. So what is the probability that one of these students likes dogs? Well, that would be this whole group of students right here, those 20. So the probability of a student liking dogs is 20 out of the total, 25. So it's 0.80 or 80%. What is the probability that a student likes dogs given that they like cats? So if I'm telling you they like cats, I can only look at the people in the yellow column, all right? I have to ignore the people who don't like cats. So these 9 people don't count for my problem, only these 16. Well, how many people like dogs? 15 out of the 16. So 93.75%. Well, I could ask you, is liking dogs independent of liking cats, and why or why not? Well, if these two were the same, and they don't have to be exactly the same, like if this was 78%, I'm like, pretty close. But you got 80% here and 94% here practically. So no, the probability of liking dogs is definitely higher when we know they like cats. All right? So those are not independent. So we are dealing with dependent probabilities here. All right, so what's the probability a student likes cats? Well, how many people like cats? 16 out of how many? 25. So that would be 0.64 or 64%. What's the probability a student likes cats given that they like dogs? So we have to, if they like dogs, we're in this blue universe right here. So how many of those people like cats? 15 out of 20, or 75%. And you can see that liking cats and liking dogs is dependent again because the probability of cats is higher, liking cats is higher if we know they like dogs, all right? Still lower than liking dogs, which is true. I find more people are fond of dogs than cats. Me, I'm honestly a cat person. I like dogs, but they're a little annoying. All right, so you pick 2 students randomly from class. All right, so now we're getting into the compound events because we're going to go 1 student and then another student. Before, we were only talking about picking 1 student, which is the easy case. So we're going to pick the probability that neither likes dogs. Well, so how many people don't like dogs? Well, there are 5 people out of 25. But here's what happens. I have 5 over 25 here. Why don't I have 5 over 25 here? Well, if I pick that first kid who doesn't like dogs, how many people are left that don't like dogs? 4, all right? Out of, and there's only 24 people left. So you'll get 20 over 600, I believe, and that will basically be 1 out of 30. So probability that neither of the students likes the dogs is 1 out of 30. What's the probability they both like dogs? Again, this is another dependent situation because the probability the first likes dogs, that's just our basic probability. But we've taken one of the students out now, and there are only 19 students left who like dogs out of 24 students left. And when we multiply all of that out, we get 19 out of 30. So what's the probability the first one likes dogs, but the second one doesn't? So people who like dogs are 20 out of 25. This 25 is automatically going to change to a 24 because we've taken 1 student out, all right? How many people don't like dogs? Well, that number's actually going to stay the same. The whole probability changes, all right? 5 over 24 instead of 5 over 25 because we took somebody out. So this number is really what's changing because we're keeping the 2 students, all right? And we multiply that, it's 1/6. The probability the second likes dogs, but the first doesn't, is, so the first doesn't like dogs, that's 5 out of 25, like what I was trying to tell you here, right? But it changed. Now, instead of 20 out of 25, it's 20 out of 24. So you can see how these are very similar. And the only thing that's really changing is that 24 on bottom. So if I'm surveying students, how many students might like dogs if I'm picking 2 students? Well, I could have up to both of them like dogs. I could just have one of them like dogs, or 0. So we're going to get to a probability model. All right, so I went ahead, you don't have to rewrite this down. This is just for my reference. So these 2 people don't like dogs. So sad. All right, so I'm going to make my table. I could have 0 students like dogs, which in this case is a 1 out of 30 probability. I could have 1 student like dogs, which is going to basically be 1 out of 6 plus 1 out of 6, which is 2 out of 6, also known as 1/3. All right. And I have the probability that both of them like dogs, and that's 19 out of 30. Does this model make sense? Are these all the possible outcomes for 2 people? Well, let's go ahead and check by adding these up. So I have 1 out of 30 plus 1/3 plus 19 out of 30. I'm going to combine these 2 because they have a common denominator. And I'll go, oh, that's just 2/3, right? 20 out of 30 is just 2/3. You see that? And 2/3 and 1/3 is 1. So yes, it does make sense because they add up to 1.